Next, we'll start the review of linear system theory as needed by this course, and the first item will be continuous time linear dynamic systems, and we'll discuss the concepts of controllability and observability. The state space representation of a continuous time linear system is x dot is a of t xt plus b of t ut. Xt is the state. It's a vector of dimension nx. U is an input or control vector of dimension nu. A is an nx by nx matrix, that's a system matrix, and B is the input gain, and as the notations indicate, we assume a system which might be time varying. This is called the dynamic equation or the plant equation. And the output of the system is, and again, a vector z of t equals c of t x of t, where c is a known nz by nx matrix called a measurement matrix. So we'll have an output, again, by a possibly time-varying matrix that relates the state to it, and the dimension of the output, in most cases, nz, will be smaller than nx. So this is the output equation or the measurement equation. Given the initial condition of the system x at some time t0, the reference time, and the input function u in the interval t0t, which is a function u of tau with tau between t0 and t, you can compute the future output at any time t greater than t0, that's z of t, a function z of the initial condition, the input function within this time interval, and the points defining this time interval. Initial point is t0, final point is t. Now, the state of a deterministic system is defined as the smallest dimension vector x that completely summarizes the past of the system. In many cases, we will deal with simpler versions of systems, namely that are linear and time invariant. The same equations as before, except now a of t is a constant matrix A, b of t is b, and c of t is a constant matrix C. The first concept of interest is controllability. Even though we are dealing with estimation problems, information extraction, it turns out that controllability does play a role in ensuring the existence of solutions. So that's very important. This is why we need these concepts. If we have a continuous time deterministic system, we'll go later to stochastic systems. Right now we stay with deterministic. We say it is completely controllable if, given an arbitrary destination point in the state space, there is an input function that will bring the system from any initial state to this point within a finite time. If the system is linear and time invariant, the controllability condition turns out to be as follows. The pair AB, A is the system matrix, B is the input gain, is said to be controllable if we have a controllability matrix Q sub C consisting of B, AB up to A to the nx minus 1b, if this matrix has full rank, in which case the rank would have to be nx because the dimension that you can see, the number of rows here is nx, the number of columns is more. So this is the lower of its two dimensions. The other one is nx times nu. So if this matrix is of full rank, then there is a control function which can bring the system from an arbitrary initial point to an arbitrary finite point within a finite time. The second concept is observability. We could take the same continuous time deterministic system and we say it is completely observable if its initial state can be fully and uniquely recovered from its output when we observe it over a finite time interval and obviously we need the knowledge of the input at the same time. Now, remember, we are talking about a deterministic system. Therefore, knowing the initial state is as good as knowing the state at any time, because the state at any time together the state at any time can be obtained from the initial condition together with the input, in the intervening time. So, using the output, which is in general a vector of a lower dimension, we can recover the state perfectly. So that's a concept of observability, that every component of the state somehow shows up uniquely in the output and can be fully recovered. In the case of a linear time invariant system, the observability condition is that the pair AC, A again is the system matrix, C is the output or observation matrix, is observable. The observability matrix, Q sub O, consisting of C, CA up to C to A to the nx minus 1, would have full rank nx, and clearly nx is the number of columns in this case. Let's take an example. This example is a double integrator. Typically, it does arise when you have a moving object and with some acceleration. Single integration takes it into position. Another integration takes it into, single integration takes acceleration to velocity. Another integration, velocity into position. So the double integrator maps acceleration into position. And here's the state vector for such a system. Position and velocity. We're talking about motion in one dimension for simplicity. The state space representation of this system will be given by this matrix A. It has two zero eigenvalues, and a zero eigenvalue means an integration. Transfer function has, it's really constant, or 1 over s square in the Laplace domain. And the input u enters into the second component. That is really the original equation number 7 we have here. This is the second equation that we have, because this is the derivative of the velocity. Now, if we look at the controllability matrix in this case, it will be BAB. It turns out to be a square matrix. It has, as you can see, determinant equal to -1. So clearly it has non-zero eigenvalues. It has full rank. It is completely controllable. Now, the input u enters directly only into the velocity component of the state. It still has the capability of controlling both state components, which means given u as an acceleration, you can bring the system to an arbitrary point in the space, in the state space, at a given velocity and a given position within a finite time. That's very important. So it is not required that the input enter directly into each state, but indirectly via the dynamic systems equation, it should be able to manipulate, to control the state exactly and bring it to any desired final point in the state space. Now, let's look at the other problem, other situation. Observability. Z is Cx, assume we observe the position. Means that the vector, row vector 1, 0 multiplied with the xi dot components of the vector x picks up only the position, the xi component. So what we have is position, only observations. The observability matrix, we can write it C, that's the 1, 0, and CA, that's a 0, 1. Again, this matrix has full rank equal to 2, and the state is completely observable. Clearly, if you observe position, you can observe already one of the states. However, you can ideally think of this that by differencing the positions at two different times, you can obtain the velocity. So this is a little bit more delicate or a little more subtle how it works exactly, but that's the basic idea, that observing position for the system allows you complete state observability. And here's another example. Now we observe only velocity. Z is a Cx, but now we have a different C. It's 0, 1. The velocity is what we observe. Now let's look at the observability matrix for the state vector, again given by the same expression, C, you put it here 0, 1, CA turns out to be 0. What is the rank of this matrix? Deficient, not 2, only 1. The state is not completely observable. And the reason is that with positioning observations, we do get information about velocity. With velocity observations, we don't get any position information. Effectively, knowing the velocity will never tell us the initial position where this object might have started. And this is now the intuitive interpretation. It is very important to understand with intuition the mathematical concepts. So we have this example now that position allows complete observability in this case, and velocity does not. Most of the material we are going to cover will be discrete time systems, for the very simple reasons that computers like to operate in discrete time. So we need the same concepts, the same equations, state equations, and concepts of controllability and observability in discrete time. Now what is important is that many systems are naturally defined with dynamics in continuous time, and the observations are done in discrete time. So we have to connect between the two. And we'll do this later in the course, how to discretize a continuous time system. Right now, we'll assume that we have given a deterministic linear dynamic system with the state equation of the form xk plus 1 is f of k xk plus g of k uk. Again, xk is the system state, dimension nx. F is called now the transition matrix, is an nx by nx matrix. U is an input or control of dimension nu, and G is the input gain, an nx by nu matrix. And it is time varying because F might depend on K, G might depend on K. Practically speaking, systems which are time invariant but are sampled at unequal intervals do become, in discrete time, automatically time varying systems. The output equation, z at time k is h at k xk. So we have the output vector or observation or measurement, dimension nz, and h is the measurement matrix nz by nx. For the sake of generality, it is shown as time varying. In some cases it is, others it might not be. Now, again, as in continuous time, we define the state of the system as the smallest dimension vector that completely summarizes the past of the system. In this case, the output at any time j greater than k, k is the present time, j is the future time, can be determined fully from xk and the intervening inputs. That's a sequence now. So z at time j will be function z of the time j, the x at time k, and the intervening input sequence, that is from uk up to and including u j minus 1. It's very important to understand the concept here that state is something that completely summarizes the past. And the reason we can afford this luxury is that we have deterministic systems. When we go to stochastic systems, we will not have the ability to completely summarize, but to summarize in full in a probabilistic sense, rather than in a deterministic sense. So we'll come back to these concepts, and this I wanted just to stress this issue right now. Now, a discrete time system is linear and time invariant if is described by the equations we've just seen, but f of k is a constant f, and similarly g of k is a g, and h of k is h. The controllability, it turns out, both in discrete time and in continuous time, the concepts are the same, but more surprising, even the equations will be almost the same. So, a discrete time deterministic system is completely controllable if, given an arbitrary destination point in the state space, we can obtain an input sequence that will bring the system from any initial state to this point in a finite number of steps. So this is really the counterpart of the continuous time definition. If we have a linear time invariant system, the controllability condition is that the pair Fg, these two matrices, F is the transition matrix, G is the input gain, is controllable. Namely, the controllability matrix Q sub C, G, Fg, f to the nx minus 1g, has full rank nx. And if you go back to the continuous time case, you'll find out that we have essentially the same expression with the gain here, and instead of the transition matrix in the discrete time, what we have is the continuous time system matrix A. So there was a B here, an A, B, and A to the nx minus 1, B. Observability. A deterministic system is completely observable if its initial state can be fully and uniquely recovered from a finite number of observations of its output and the knowledge of its input. Note that since the system is deterministic, knowledge of the initial state is equivalent to knowledge of the state at any time. You can propagate through the deterministic equation if you know the input, both backward and forward, it turns out. Thus, using the input and the output, which is in general vector of a smaller dimension nz less than nx, you can, in the absence of noise, recover the state perfectly. And it turns out this perfect recovery ability in the absence of noise allows us to do recovery, quote, as much as possible, to the extent possible, unquote, in the case of a stochastic system. So what we can do perfect in the deterministic case, we can do optimally in some sense, as we'll see in the stochastic case. If you take a linear time invariant system, the observability condition is that the pair FH, that's transition matrix and output matrix, is observable, and we have the observability matrix Q sub O, H, HF, HF to the nx minus 1, and this should have full rank, which is nx. Okay, this much is what we need from linear system theory. The continuation now will be a brief review of probability theory, from which we need a little bit more, so we'll take a few additional lectures. I think it's beneficial to start probability from the basic definition, which starts with events and the axioms of probability. Consider an experiment, a process with random outcomes. In this case, we define an event as a collection or a set of such outcomes. And we said that such an event occurred if the outcome is one of the elements of this set. As an example, we denote by A an event in such an experiment, say a die rolling experiment, where an event can even outcome is an event, that's 2, 4, or 6, 5 is another outcome. And we can define an event consisting of a single outcome or a set of outcomes. It's important now to introduce the so-called sure event, S, in the experiment, which in the die rolling would be any number between 1 and 6. It's called sure event because obviously whatever the outcome is, it will be one of the elements of the set. Therefore, the event S, any number between 1 and 6, would occur at every run of the experiment. Then the probability of an event is defined as follows. It is a number. In more mathematical terms, it is called a measure, and it would have to satisfy the following 3 axioms of probability. It is non-negative. Probability of the event A is greater or equal to 0 for any event A that we want to talk about. Second axiom, it is unity for the sure event. The certain event, probability 1, 100% certainty, sure event, that is what we mean by it. Third one, and that's very important, it is additive over the union of mutually exclusive events. That is, if the events A and B have no common elements, their set intersection is the empty set, then, and there are several notations we are going to use. A intersection would be, this is the set notation, same thing as A and B, that's the logical notation, or the shorthand logical notation is A, comma B, is empty. Then the union, which is the logical OR, has probability P of A union B, which is P of A or B, can be written also as P of A plus B, is the sum of the probabilities of the event A, P of A plus P of B. Clearly this makes sense. There is no overlap. One occurs or the other occur. The probability that one of them occurred will be the sum of the 2 probabilities. From this it follows that if we define A bar as the complementary event to A, P of A is 1 minus P of A bar, which is less or equal to 1, like any probability, cannot be more than the sure event, must be greater than 0, because their sum is the sure event, and therefore the sum of their probabilities equals 1 in view of the fact that their intersection is empty. A and A bar being one, being the complement of the other, obviously have 0 intersection. Now, the empty set is the complement of S. Clearly, the probability of empty set occurring is 0, and that's why it is also called the impossible event. Why? Because whenever you run an experiment, something happens. The nothing never happens. Okay, a number of additional definitions of probability are around, and I would like to mention 2 of them. A relative frequency or measure of belief interpretations of probability are alternative, even though not rigorous, ways of introducing the concept of probability. Relative frequency really can be used to assign probabilities to certain events when their occurrence probabilities are the same. So what you can do is use that relative frequency experimentally and figure out what the probabilities are. Now, measure of belief is what I would call engineering common sense way of assigning probabilities to events. And in several systems, it's very useful to be able to assign probabilities based on our understanding of the physics of a process. Now, it should be noted also that probability is a scalar quantity that is physically dimensionless. It's just a plain number between 0 and 1, and it will be contrasted very shortly to the probability density function, or PDF, which, while a scalar, has a physical dimension. Let's consider some examples. Die rolling experiment has a space of outcomes of 6 phases, phase 1 through phase 6. The events are subsets of this, S. Event F1 can be phase F1. Event that the outcome is an even phase is F2, F4, F6. Event that I is greater than 2 but less or equal to 4 will be phases 3 and 4. The sure event, any phase, that's S. Really, the sure event and the space of outcomes are the same, because you get one outcome from that space, therefore that space is the same as the sure event. The impossible event, an example here, is I less or equal to 1. That's possible, because I1 is feasible. Even is feasible, but not both at the same time. So this is impossible. This is an empty subset of S. You cannot find in the space of outcomes an outcome which has a phase number less or equal to 1 and happens to be even. Now, if we postulate a fair die in which each outcome or phase is equally probable, we have from axioms 2 and 3 that the sure event's probability is 1. We know that. But what is the sure event? Is the union of the 6 single phase outcome events. That's cap F sub I, means the outcome is little fi, that's phase number I. So cap F is the event, little f is the outcome in this case. So this is the sum of the 6 probabilities of each phase coming up. If it is a fair die, then each phase has the same probability, and we end up with 1 equals 6 p of fi. Therefore, for each I, the probability of that event is 1 over 6. Similarly, using axiom 3, probability I even is the union of F2, F4, and F6, and they are non-overlapping. Therefore, with axiom 3, the probability of this union is the sum of the individual probabilities of those events. Axiom 3 really was defined for 2 events. It is easily seen how from 2 you can go to 3 and to any finite number. Now, random variables and probability density function. We talk about a random variable as a real valued function, takes values on the real line, which assumes a certain value according to the outcome of some random experiment. The value taken by a random variable is called the realization of this random variable. The probability density function, PDF, of a scalar continuous valued random variable x at x equals psi. So x is the random variable, psi is the point at which we will evaluate its PDF, is given by the probability the outcome x is between psi minus d psi and psi in this small interval divided by the length of the interval. Clearly the probability is a non-negative quantity, so you end up with a non-negative value here, and at the limit what we get here as the interval gets smaller and smaller is a density. It's the same thing as the mass density over some kind of a bar. And what we have is, notice the numerator will be a number because that's a probability, and the denominator will have the physical dimension of the quantity we are talking about, d psi, like the length of the interval. Typically, there is a more complicated notation and a simplified notation. P sub x at x is just P of x. So what we really do is have the probability density function of the random variable x at location x, just denoted as P at location x, and the name of the argument here really defines the function. So we use this simplified notation unless we have to indicate to whom the PDF belongs if the argument happens to have a different symbol. The term density is sometimes used instead of PDF. It also follows from the third axiom that we discussed earlier that the probability of x being in this interval between eta and psi is just the integral of the probability density function over the interval from eta to psi, and this also follows from the definition of the probability density function as well as from axiom 3. Now, there is another function, cap p sub x at psi, which is the probability of the event that the random variable x is less or equal to the number psi, and this is the integral from minus infinity to psi of the probability density function, now written in the simplest possible notation, px dx. This is called the cumulative probability distribution function of x at psi. Sometimes it is referred just as the distribution. So we use density, we use distribution. That's shorthand designations. Now, the event x less or equal to infinity is the sure event. So p of x less or equal to infinity, any random variable that takes value on the real line would have to be less or equal to infinity. Therefore, the integral of its density function from minus to plus infinity is unity. So that's a sure event. Therefore, we have what is called the normalization property, namely that the total probability mass is 1. Otherwise, it's not a proper density. So a proper probability density function must integrate to unity over the entire real line. Let's consider another example. A uniformly distributed random variable in the interval AB will be symbolically denoted x distributed uniformly in the interval AB. Its probability density function is denoted as u with argument x parameters AB. So here is distributed as, here is a function. It turns out that as long as x is within this interval, this is 1 over the length of the interval, that's 1 over b minus a, and it is 0 outside. So this will be two similar but not the same notation, because again this is to be read distributed as, and this is a function now, and it is a constant for x in this interval and 0 outside. This is why it is called a uniform random variable. The cumulative distribution function of this, p sub x of psi, is if psi is to the left of the point A, it cannot be there because it must be in the AB interval. Within this interval, if you integrate, is a psi minus a over b minus a, so that's really a straight line moving from 0 up to 1, and at psi equal b it becomes 1, and then it stays 1. Now, a Gaussian or a normal random variable with parameters mu and sigma square. The names of these parameters, I will mention them, but hopefully you are familiar with them. We'll reintroduce them in any case. Mean and variance, we'll discuss them in more detail later. We denote this symbolically. X distributed normally with mean mu, variance sigma square, and normal is the same thing as Gaussian. The PDF, or the density, or the probability density function of such a random variable, its p of x is Gaussian, the argument is x, and has these two parameters, mu and sigma square, and the expression of this density is a constant here, come back to it in a moment, e to the minus x minus mu square over 2 sigma square. This constant guarantees that the integral from minus to plus infinity of this density equals to unity as it should be. Its cumulative distribution function, cap p sub x at psi, is integral from minus to plus infinity. This is the probability that it is to the left of the point psi, which means between minus infinity at psi on the real line, is the integral of this density times dx. Now, we can modify the integral by a small change of variable, introduce a new variable eta, which is x minus mu over sigma. Then the integral changes, the limits will be from minus infinity to psi minus mu over sigma, and in the exponent we have a minus eta square over 2. Outside there is a 2 pi, this will cancel the sigma, and this density that we have here is a standard Gaussian density. Argument is eta in this case, and by standard mean we mean that the parameter mu is 0, the mean is 0, and the variance is 1. And this is what is called the distribution of a cap G will denote a standard Gaussian cumulative distribution function, which is the probability of being between minus infinity and this point, and the upper limit will show up as the argument of this standard Gaussian distribution, psi minus mu over sigma.